Okay. You need the blind closed. The blind. Yeah. Okay. Right, guys, we'll get started. So, can you write that down? Scatter plots. That's what we're having a look at now. So, this is quite a common graph in research and when you're doing experiments, because I'm sure, yeah, you did this in biology, didn't you? Enzyme activity and temperature, pH, was it? And did you plot the two? Yeah? No, not yet? You will, though. So which way around will you place them? Which on which?
What? No. Temperature on the x-axis. Yeah, enzyme activity on the y-axis.
And, oh, that's measured in a volume, wasn't it? So it's some kind of volume in units of centimeters cubed, and the temperatures in units of Celsius. And roughly how many points did you have to plot in this experiment? About 6, wasn't it?
8.
Okay.
6. 8.
Was it? Okay, it doesn't matter. It's roughly something like this. So, do you know yet what type of graph you'll get when you plot them? Will it be linear? Yeah. It might taper off at the end. Oh, okay. So you already know that it'll probably curve back down. Yeah, okay. So this is an example of a scatter plot, is where you plot your data points on an x and a y axis. And the reason you'd want to do that is to see if there's a relationship between x and y. So here, this graph makes it clear that there is a relationship. What type of formula, what type is the relationship here? Well, we all can see it's not linear. Yeah? What would we say it is? I'm looking. I wouldn't say exponential, no. Because I think this is going to keep going back down, isn't it?
No.
Yeah, so what formula is that? What's it called? Oh, come on, guys. Yeah, but what's the name of the formula? Quadratic?
Yeah.
She's telling me no. No, I'm pretty sure of this now. I don't think they would give me my maths degree if I didn't know this. So a quadratic going down like this. Okay? But of course there's many other possibilities. The only one we really will look at in this chapter is the linear case, when it's linear. Now, in fact, a lot of these scatter plots will be at least linear for the beginning. So like even in this example, you can see that, well, it's roughly linear, but you can see at a certain temperature, it's no longer reasonable to say that it is linear. So we're really focused on looking at the linear part here. Okay? Yeah. Now, sometimes in the exam, they will actually test that you understand that. So they might have some example of, like this, volume and temperature. And they might say a question for 1 mark. Why is it inappropriate to extend this graph into higher temperature values? And the reason is, well, we don't know if the graph will stay linear. In fact, in this case, we know it won't. What will happen to the volume? It will start to decrease. So, if we extend our graph too far, we see we're way off the mark here. Okay? So, usually for the linear, just it's worth noting in your notes that most scatter plots are linear in certain ranges. So for this particular question, it's only really linear from here up until, I'd say, maybe at most this temperature. And from here up to about here. Okay? Yeah, so far okay? Yeah. Okay. Let's continue now. Not yet? Okay, come on. Can you think of some scatter plots that you can feel confident in saying that they'll be linear? That maybe you've done in other classes? Pressure and temperature. Yeah. What about anything in biology or chemistry? Have you done those formulas in chemistry? Like pressure is proportional to, yeah? Yeah, you've done this in chemistry? Yeah. You have one you have pressure and, or I'll put it the other way, temperature and pressure. That would usually be straight, wouldn't it? What else?
Temperature and volume.
Yep, yeah. You've done these with Lorraine, or you just remember them? Okay, what have you done, or have you done anything this year in chemistry or biology where you know you'll have a linear graph?
No.
Really, it's just this one?
Waves. Yeah. Like just linear, no plateau, and just straight as we did.
Most of your graphs don't stay linear, is it?
Yeah.
They plateau or go back down. Yeah, okay. Yeah, okay. Now, can I scroll down now? Yep, okay. So what we're looking at today, really three things. How to draw these graphs, roughly. What's the meaning of the values on the graph, and like how to interpret or how to predict the results here. So can I scroll down? Yeah. So the first thing we'll do is we'll practice how to draw these graphs. Now there is actually a way to draw them. I'm not going to give you lots of points, so I'll just give you, we'll just make up 4 points as an example. It's the same idea for as many number as points as you want. So here's our data. I'll just make 4 values. We might as well keep it the same. What did we say? Temperature, wasn't it? Temperature in Celsius and volume in centimeters cubed. What type of temperature values were you using? Like what size? From what to what?
We went from 0 to T. That 0 forces.
You did use ice. Use 0. Yeah, okay, great. 0 and... So I'll just do 0, 20, 40, 60. Yeah, I'll just do that as an example. And what type of volumes were you having? What size numbers? Are we talking tens or hundreds or tens? Okay. So I'll just make up some numbers. 40, 50, 55, and I'll just say 60, something like that. Just make up some examples. Okay. Oh no, I'm not trying to do exactly what you did. I just want to make up some numbers similar to what you did. Okay, so we want to make the scatter plot. Well, that first part is actually pretty straightforward. We just need our graph here. Now, this here has to be 0, 0. And we're going up to 60. So I'll go 10, 20, 30, 40, 50, 60. 60. And this is temperature in Celsius. And then the volume also is going up to 60. So I'll go 10, 20, 30, 40, 50, 60. And this is volume in centimeters cubed. Right, our first point is 0, 40, isn't it? Second point is 20, 50. What's our next one? Sorry, is that quite at 20? Yeah. Next one is 40, 55. 10, 20, 30, 40, 55. And then the last one is 60, 60, which is there. Now, I know it looks like it, but I don't ever expect these to line up perfectly in a straight line. I mean, I think, yeah, I can't really do it with a pen, but it's probably, you know, it's going to be something like that. Okay. Anyways, what we want to do now is how can you draw a good line. Actually, does anyone know the name of this line? Line of best fit. So how can we draw a good line of best fit? Well, we have a good intuition of what's a bad one. So this would be a bad one, wouldn't it? Yeah. As would this one and this one and this one. So mentally, what are we trying to do? We're trying to capture as many points as we can. What's good to note, though, there is always one point I know that should be included on the line of best fit. And you should always include, does anyone know? Which point? The first one, like 0, 40? No, not that. Oh, the last one? 60, 60? No. One of the middle ones? Kind of, not quite. Line of best fit, you should always include a point which I actually didn't mention. You should always include the mean. So on this graph, there's one point missing, which I'll draw in a different colour. It's the mean temperature and the mean volume. So what is the average here? 60 plus 40 is 120 divided by 4. Is that 30? So the mean temperature is 30. And then here, what's that? 205. What's that? 52.5? The mean volume? Listen, how can I do this in my head quicker than you can with a calculator? By the time you've taken this out now, come on, come on. Is it 30 and 52.5?
Did you count the 40?
Yeah.
51.25.
4 numbers.
Yeah, but zero.
So, 0 is a number.
No, we should not like include.
I never said that. Did I ever say that? No. 0 is a number. Yeah.
51.25.
51.25. I was wrong here. 51.25. Yes?
Yeah.
Thank you. Now, let's plot that. 10, 20, 30, and 51.25 would be about here. Whatever line you draw, you absolutely must include this point. Now, there's actually a mathematical reason for it, but we won't go into that. We'll just say that you're always guaranteed that the mean is on the line of best fit. Okay, so we need to think about, okay, what line should I draw? Which way should I draw it? Well, a rough guideline is you should try to have the same number of points above and below the line, roughly. So obviously, you know, okay, this guy here does technically work. How many points are above it? 2. And how many are under it? 2. But we can kind of tell, well, this we could turn this a bit more, couldn't we? And likewise, like this here. What would be great is if we could get some of the points on the line as well. So I think what I will try and do is I can have, if I draw the line here, I can have these 2 points just about above, touching it.
Take 3 points.
And then, see, I'm not too happy about that. That's a bit too far. I might now try and pass through this point. Again, but 2 I was under it, so I think maybe the first one was better. Now, I think that actually is the best one because I think this guy here is lower than it should be. For example, here you notice that the volumes are a good bit more than the temperatures.
Yeah.
Whereas when I get to the last temperature, it's 60. So this value is a little bit smaller than perhaps you would expect from looking at the previous tree, right? Yeah. So actually this being quite low and the line being quite high is probably mathematically the best model here. So I think this really is the best fit in line I can fit with the data here. I've got 2 points above, 2 points below. 3 of the points are close to the line, and the one that's furthest away has a reason to be furthest away. There's something a little bit off about this last value. And we kind of know why that value is off, because what's about to happen in the graph?
Plateau.
It's about to plateau and decrease. It's possible that the graph is already beginning to decrease, that perhaps the graph is going like this already, you know. So, for this lesson, we don't have to be exactly precise, but we can still be pretty precise here. Okay. Now, the next thing we'll have to do is write down the equation of this line. And again, we're just estimating it from the graph. So the formula we know is y equals mx plus c. In this case, it would be v equals, not mx, but mt plus c. Yeah? Now the c is the easiest point to get. How do we get the c? Yeah, the intercept. So that looks like it's a little bit under 10, 20, so about 39. Okay, so I'm going to say the c is roughly 39 centimeters cubed. Roughly, right? Maybe it's 38. Okay. Now, how can I get the slope, the gradient? Yeah, well, I could use 2 points. Yeah, well, I need to use 2 points, okay? And right now, I've already committed one of the points to be on the line. Should I use one of the red points? No, why not? It's not on the line anyways, but I do know that this point is on the line, don't I? I'm guaranteed it. The 30 and the 51.25. Now, because I'm saying the C is 38, I'm committing to the fact that I think 0.38 is on the line. Because otherwise, if I didn't think that, then I shouldn't be saying C is 38. Yeah? So, now that I have 2 points, I can calculate the M. You know how to calculate the M from week 1. It'll be 51.25 minus 38 over 30 minus 0. So what do you get for the M here? 0.442. Yeah. So what can we say our formula is for volume? We think volume is equal to 0.442 times the temperature plus 38. Now we'll continue in a moment. I'll let you write that much down.
Can you use the mean since it's on the line?
Mm-hmm.
So the points you use for the mean, can you just substitute it in? So your X.
Oh, I see what you're saying. Sub it in. Yep. Yep. Yeah.
How did you get the blue line?
How did I get the blue line?
Yeah.
What do you mean, how did I get the blue line?
I mean, I know that like you get the mean,
Yeah?
but how did you plot?
I'm not sure what you're asking me. Like, I know what you're asking me, but I'm not sure what the problem is, because I just showed you.
No. So now you get the mean average.
Yeah.
The time and
Yeah,
the
yeah, yeah, yeah.
Okay. It's 30 and 51.
Correct, yeah.
So 30 is the time.
The temperature.
Yeah, and the V is the volume.
Yeah, yeah, yeah.
Okay, then you plot the point.
Yeah.
Then how did you know like the curve? Like not the curve, like
The slope.
how the line.
Yeah, well, my guideline is, what's my guideline here for drawing the line? There's 4 points, 4 red points. So I should try to draw 2 up, above, and 2 under the line. Do you know what I'm saying? Like these red points, are they above or under the line?
Above,
Yeah, and these ones?
under.
Yeah. So I'm trying to draw the line so I get this. And if possible, I should try and have some of the points on the line, even. Yeah?
Is it always to like the 2 points? Above?
No, like, I mean, I have 4 points here. So, for example, if I had 10 data points, then what would I be trying to get?
5 above.
5 above and 5 below.
Yeah.
Roughly. Now look, Hazza, if I gave this question to 10 students, I'd expect 10 slightly different answers. Because it's only, it's only a guideline, a rough estimate here. Yeah? Can I scroll down? Yeah? Now, in the exam, a typical second question here, for example, if this was an exam question, part A might be draw the scatter plot, and part B might be estimate the line of best fit. And then part C, after you do the line of best fit, they would often ask you to interpret the coefficients here. What does it mean for this problem to say that the gradient is 0.442 and the intercept is 38? So, taking this as an example, let's see what we can say. Let's start with the 38. That's a little bit easier. What can we say about the 38? Yeah, but in the context of this story to do with volume and temperature. Well, the intercept is 38, and what value of temperature is the intercept?
40.
No.
0.
0. The 38 was when you had 0, wasn't it? Yeah?
Yes, sure.
No, hang on, guys. Okay. In the experiment, what was the smallest volume recorded?
0. Oh, this one.
Hang on, I'll say this again. In the experiment,
This one.
yeah, this one. Yeah, oh, sorry. Okay. This one here. In this experiment, the smallest recorded volume was 40. Now, this 38 is outside your data range, so it's kind of a bit like a prediction. What you're saying is, we predict at temperature 0, what volume would we expect to see?
A minimum of 38.
Yeah, the 38. Okay. This 38, this intercept of 38, this is what you might call the predicted volume at T equals 0 Celsius. Okay? So, what we've actually done is we've actually made a prediction. We've taken our data, we've modelled it, we've fitted a line to the data, and now we've already made a prediction. We're predicting that at 0 degrees Celsius temperature, we'll have a volume of 38 centimetres cubed. Okay? A little bit trickier now is this. The 0.442. Yeah. There's a standard sentence here for this one. But what does the 0.442 mean? Again, in the context of temperature and volume. Yeah, go on. As temperature increases, yeah? You're very close. You just need the right words. You're very close. Not coefficient, though. But you're close. So, getting closer. So what we can say about the 0.442 is this. For each unit increase in temperature, the volume will increase by 0.442 centimeters cubed. No, I don't need to say that because at the start of my sentence I said for each unit increase. So that captures what you said of the per unit Celsius. Yeah. So if you were to use that, you'd have to use it at the end of the sentence if I didn't use this at the start of the sentence. Yeah. But actually, it's kind of standard, Carulo, to write these sentences in this structure where you start off by saying, for a unit increase in x, the y will see a blank increase. Yeah? So really what this is saying is, if I had two people and one of them did an experiment at a temperature of 50 and the other person did it at 51, I know because they're 1 unit more in temperature that they'll be 0.442 units more in volume. Yeah? Yeah. And what's the only difference if it was a negative? There's a decrease. That's the only difference. Yeah. Okay, there is one thing left to show you with these lines of best fits. So just let me know when you have that. You got that? Can I scroll? Yeah. Yes? So I just want to go back to this table for a moment, and I'll just put a new table over here. Just make it a tiny bit different now. I'm still using this table though. Temperature in Celsius, 0, 20, 40, 60. And here, what I'm writing here is V hat. I'll explain what that is in a moment. Centimeters cubed. Has anyone seen this notation before, the meaning of it? What do you think? No? No. So, the V hat is the predicted volume. If this blue equation was true, then I would like to know what the volume would be when the temperature is... oh, hang on. This is already 0, isn't it? So, oh, yeah, no, that's fine. Yeah, 0. So, when the temperature is 0, what is the volume? 40. That's what we observed. However, if we were to use this formula, what would be predicted volume if the temperature was 0? 38. So straight away, we see that there's a small error. But this should not surprise us because the line is not fitting the data perfectly, is it? It's a little bit off. So, the 38. Now, using your calculators, can you sub 20 into this formula and tell me what the predicted volume should be when we have a temperature of 20? Okay, I'll just do one decimal place, 46.8. Right. And at 40?
55.7.
And finally at 60?
64.5.
Like this. Okay. There is a way to calculate a sort of error here in our model. Okay. These four numbers here, would we like them to be similar or different to these four? Well, we'd like them to be similar. In fact, what would be the best situation? You know, what would be the best situation for these four values? If they were the same as these four, wouldn't that be best? Well, they're not. So we calculate something here. What I'll do is I'll put it in another table here. You can put it beside here if you want. We calculate something called residual squared. It's a little bit like error squared. What you do is you look at what you observed, you looked at what you predicted, and you look at the difference. What's the difference between 40 and 38? 2. And you square that difference. Now the reason you square it is because, simply put, you don't care if it's a plus or a minus, because if you're 2 under or 2 over, both are just as bad, right? If this was 42, would that be better or worse? No, it'd be just as bad. Because 42 would mean you were 2 over, whereas 38 means you're 2 under. But, I mean, it doesn't matter. You're 2 away, okay? So mathematically what people do is they square it, so they don't care about the plus or the minus anymore. Now, what was the difference between this and this? 3.2, wasn't it?
Yeah.
So 3.2 squared?
10.2.
10.25.
Okay, can you get the next difference and square it, please? 0. Really?
Yeah.
Okay, nice. And then the next one?
0.25.
Ah. Which has the biggest residual? The last one. Is that, again, is this a surprise? No, because we can actually see it's quite off the mark. So the last thing to do here is just add those 4 numbers together. And this is the what you might call the total residual. Sorry, residual is a word that means like error, mistake.
But if you can I do that column also like 1 decimal point?
Say again?
Like 10.2, 0.55.
Yeah, what are you asking me? Can you do?
Like 1 decimal point.
Oh yeah, I'm just I should have stuck to 1 if the previous one was 1. What's the total here? Guys, what's the total? About 35, is it?
34.98.
Okay, so it's about 35. Yeah? Now, if I had 2 students do this question, the student with the more accurate model will be the student that has the smaller or the bigger value here? Smaller. Okay? So if 10 of you did this and you had 10 different total residuals, the person who has the best fit in line and the best model for the data will be the student who has the smallest residual here. Why? Well, if this is smaller, it means these were smaller.
Yeah.
And if these were smaller, it means these errors were smaller then. And now you perhaps see the reason why we took squares. Because you might say, well, maybe someone's smaller because one of these is negative. But could any of these be negative? No, that's why we squared, to make sure they're always positive. Okay? Yeah. Now, what we'll see in maybe the next lesson today, actually, is a more accurate way to calculate these. But this is actually pretty good and pretty accurate. Let's see which ones I'll have you try for a few minutes. There's only 4, actually. Number 1 and number 4. Yeah? Is this about the line again?
No.
No, what?
I didn't get the last part, the square. Yeah,
These? What did? Oh, I looked at the difference between this number and this number, and I squared. Squared?
So what does like that sign mean?
Oh, it's just a fancy way to say residual, which means error. It means mistake. As I was saying, these 4 numbers and these 4 numbers, they should be the same. But they're not.
But now that the residual numbers, what like they are presented in the graph?
They're roughly speaking these distances.
Like the distance of error?
Yeah. That's why I was saying, Hazard, that the student who has the smaller total residual has the better model. Yeah.
The residual is what again? I'm still lost.
The difference between the predicted, the observed and the predicted. Total sum of residuals squared. Huh?
They just take the one. Four,
1 and 4. Can I close this? Yeah.
So which page? Is it 110 or 112?
Whatever the next 110. Yeah. Yeah. Scatter plot. Yeah.
How about the line of best fit? Because
Well, that's on the next page. So guess what that will be? That will be the next lesson. You understand in maths topics connect, don't you? So like, yeah. It's not like each lesson is totally random and different from the last lesson, you know.